control system. So a little outline, talk about the experimentation method we used, the background of each one, the physical control system, how to do the experimentation and results, and then finally sum it up with the conclusions. So experimentation started off with each team member was divided into range 2 to 7, 7 to 12, and 12 to 17 centimeters of water pressure. Steady state operating curve was conducted by data points, 6 trials in each range to make one steady state operating curve. And in a step response experiment, we had 3 step ups per range and 3 step downs per range. And each of those combined to make just 3 parameter graphs. So to get the steady state operating curve, we start with a change in the input power percentage, which let it reach steady state, calculate the average output in the steady state. From that average, you can take the standard derivative, multiply it by 2 to get its uncertainty, and then plot the data at one point, and then repeat for 6 times per range. The background of the control system, basically there's 3 booths, there's spray painting booths. Each one of those is pressurized to control the emission comes out of there. It's controlled by U.S. EPA, by the state and local air pollution control. It's basically ran off of a feedback control system, which controls a variable speed blower. So you have the drive, the control, the transmitter, the feedback. And our experiments were conducted with dampers 1 and 2 open, so that each spray painting booth was allowed to be pressurized. The control system, you have the input, the system, and the output. Our input is that blower motor power percentage, and the output is the booth pressure in centimeters of water. And the parameters that we obtained for the step response experiments were gain, dead time, and the first order time constant. How to get the steady state data. Each trial was operated at a constant pressure. We let that constant pressure reach a steady state, took the average of that and the standard derivative, and then plotted that data point together to obtain this standard or steady state operating curve. You can see the trend line is in purple right here, so it gave us an average output of about a little over half the input. So how to get the gain in the step response experiments. This one is a step up experiment. So basically we start off with a baseline input, allow it to reach steady state, and then quickly step it up a certain percentage to obtain the desired output, and then let that output reach steady state. So taking the average of the steady state of your baseline and the average of your steady state step, then you can get your change in the outputs. And then dividing your change by the output by the initial change in your input gives you gain. To find the dead time, we just inserted a line at the inflection point, so at the steepest slope of your step, and then took the horizontal distance from where your step initially started. To get the time constant, you let tau and t equal each other so that e to the t is 1, or e is to the 1. So then your tau is going to be 0.632 times this change in your input. So if you take your change in input, multiply it by 0.632, plotted this line, and where this line hits our tangent line at the inflection where we found a dead time, we inserted a vertical line where these points meet, and the distance between this vertical line and where a dead time ended, or started rather, is our first order time constant. The results of our gain, see it right here. Our highest was at higher pressures, our lowest was at lowest pressures, and this line is the slope of our steady state operating curve, which is 0.3 times the input. These are our results for the dead time. pressure system. You can see step downs are much higher than step ups for dead time. And then the first order time constant, you can see that step downs are all relatively the same and step ups are relatively the same, but not so much as the downs. And then our highest one here is about 0.24. So in conclusion, with the steady state experiment, the average slope was 0.53 centimeters of H2O per percent. And our step response data, our gain averaged from 0.35 to 0.62. Our dead time was 0.04, 0.2 seconds. And our first order time constant was 0.12 to 0.23 seconds. Are there any questions? Is that a color? Aqua?
Use the flashlight. Yeah, which one's aqua? This is more aqua. This is more aqua, like that's more algae.
Alright, I'm Ryan Tremore. I'm on the aqua team along with Ronnie Lane and Sarah Oliver, and we are in the duct cooling system. I'm going to go over the steady state operating curve and the step response and the FOPDP modeling. We have a picture here. We don't have a diagram, but there's a picture we got. It's of a cooling fan connected to the duct heating element. And basically the fan with the input that we put in would run accordingly. So our group had an output of 44 to 50 degrees Celsius, and we were supposed to find the steady state operating curve, and for the step response system we had to find gain, the dead time, and the time constant. This is our block diagram for our system. We have a manipulated input that can be changed, and it gives a controlled output that is measured in degrees Celsius. This is one of the many experiments that we ran for our steady state operating curve, and this one was run for a length of 5 minutes with a 60% input, and it gave us around a 48 to 49 degree output. We had to compile all the data for our group, and when we had this shows that we had a -2%, or -2 times the input slope, and the reason it's negative is because the higher input we put in, the faster our cooling fan would run, in turn dropping the temperature of the heating duct. For our step response results, this is the graph of gain. We had an output. It started out an output of 75, and we had a -20% decrease, so it dropped to -55%, and it gave us a 6 degree output differentiation, which in turn, when you did the output over the input, it gave us a gain of -0.3 degrees Celsius per percent. As a graph of our dead time, the dead time that we had was 0 for all of our graphs because the input went up as soon as our step for our input changed. So we didn't have any dead time for any of our runs. For the time constant, we were given an equation, 0.632 times the output, and that gave us, and where those lines crossed with our output, it gave us a time constant of 0.7 minutes. Here's a graph of the average of our gain. As you can see, that we had they were all fairly pretty close. However, the step up on the lower level, the lower end of the runs, we don't know why, but it just kind of went haywire on us, so we don't really know. It could be a number of different reasons. Again, we don't have an average graph for our dead time because we had no dead time. This is the average time constant graph. Again, they're all about the same. They're pretty close. They run pretty close together. It varies by 0.2 minutes, except for the step up in the lower range. Again, we don't know why that test went the way it did. For the modeling FOPDT, we were given two deviation variables. We plugged them into an Excel, we plotted them, and then this is the graph that we got from that. Just to restate what I said, the reason we had a negative slope for our steady state operating curve is because as our input went up, our output in degrees Celsius went down because the cooling fan was running at a higher speed. And then these are our numbers that we got for the gain, dead time, and our time constants for step ups and step downs. And that's it. What's another color? Red, what? Buff. What's buff color?
I guess. Technically, you give it to the presenter. So I guess you use whatever you want. Is this buff?
I believe so, yes.
Never learned it.
Because it's the one that's supposed to look like tan.
Why is it like buff? What's buff?
It's the color of your skin. I've never heard of it before this class.
Yeah, me neither.
Alright, my name's Ashley Poe, and I'm on the buff team, and we studied the steady state and step response for the filter wash system. This is a flow diagram for our system. It's the filter wash system, so it has a pump with various piping to two different valves, and our experiments were run with both valves closed. This is a block diagram. So our system, we input the power, the motor power in percent, and we get a flow rate of pounds per minute out. Again, the experiments that we ran for steady state and our step responses, both valves were closed for the entire duration of the experiment, and our desired output range was between 19 and 31 pounds per minute. This is the control screen for our steady state experiment. At the various numbers are the inputs that you'll put in for to control the experiment. You'll have your name, your email address, the length of the experiment. Most experiments were ran between 30 and 60 seconds. The input power percentage, and then down here you can either have your valves closed or open, and you can set them at different intervals so they can open and close at different times during the experiment. This is our steady state experiment. This is just one representation of the many experiments that we ran. In this region, you'll see the overshoot of the experiment, and this is where the water began to be steady state. The blue line is the input in percent, so this one was ran about 51%, and the output is the red line, and it was about 24 pounds per minute out. From all of the steady state experiments we ran, we generated a steady state operating curve, and this is ours. The linear trend line of the steady state operating curve, you see the equation. Its flow rates are pounds per minute equals 0.64 times the input percent. So at any time during the experiment, you can plug your input percent in, and that should give you the flow rate out that you will expect. The next experiment we ran was step up and down responses. And again, the numbers denote entry points for the control screen. Again, you have your name, your email address. Here you have your baseline input value, which is just any type of percent you want. The time at which the step occurs, During most experiments, the step occurred about 15 seconds after the experiment was conducted. The length of the experiment, most of these experiments, again, were ran between 30 and 60 seconds. And the height of the step, which is in percentage. And down here, again, you can control whether your valves are open and closed or for different time durations during the experiment. This is one representation of our step-up response experiments. The blue line, again, is the input, and the red is the output. Denoted are your dead time and your T, and then you can find gain by dividing delta M by delta C. This is a representation of the step-down response, and much like the step-up response, it generates the same type of graph, but instead of having your step-up be like 10%, you just do negative 10%. It gives you a step-down response. So these are results from our step experiments. This is for tau. And 1 is the lower region, 2 is the middle region, and 3 is the higher region. For most of our experiments, the up and down steps were similar, except for in the higher region. This is the results from our step experiment for our gain. Again, they're pretty similar, although we do have some uncertainties that are a little bit bigger than others. This is our result for the dead time of the experiment. And our uncertainty for the step down for the higher region is pretty large in comparison to the others. So during our experiments, we noted that there were some non-standard graphs that we got when we ran our experiments. So the circles denote the unusual responses that we got conducting different experiments. Again, some more unusual responses that we come across. So in conclusion, our steady state operating curve, we generated a trend line, and that was the flow rate in pounds per minute can be calculated by 0.64 times the input percent. During our step response experiment,